Welcome back to Introduction to Machine Learning. I'm Ludwig Bothmann, and in this video I will tell you about evaluation of supervised learning algorithms in a nutshell. In the end, you should understand what the generalization error is. You should get an overview on how we evaluate performance of learners. You should know some basic evaluation metrics for classification and for regression. And you should get a very first understanding of why we do resampling. In the last chapters we have already seen how to train models. These trained models are optimal in a relative sense, which means they are better than other models. Okay? For example, we used empirical risk minimization, so the best parameter vector was the argmin of some risk given some training data. So we already know that this theta hat vector or this f hat model is the best model that we can have with respect to the training data in the training sense. But what we do not know right now is how good this model is in absolute numbers. So we do not really know how this model generalizes to new unseen test data. One idea could be to use just exactly that risk that we obtained in training, which is this, just the sum over all the losses of all the data points in the training set. But the problem is that this value can be very optimistic. So for example, here we have a polynomial regression. And if we just increase the degree of the polynomial function that we allow to fit to the data, then the fitted function will be very flexible and will more or less interpolate all those data points. So this is the best model in terms of training error. But perhaps from a more intuitive perspective, you can already see that the model with degree 5, something like this, is a better model because, well, right now we don't really know if it's better or not, it's just guessing. But the intuition is that it's not that variable and not that flexible, not that volatile, and so has better generalization properties. Which means that if we use new unseen test data and we predict the target variable out of these test data, then this model will probably produce the most meaningful predictions or the best predictions in some sense. Okay, and we have to define what this in some sense really means. Okay, so the best model will generalize well and have a low generalization error. That's where the term GE comes from. So we can define the generalization error formally as the expected loss for a new observation. This here. So the generalization error for a fixed model and somehow for a fixed loss function is the expectation of the loss of a new data point. So the problem here is that, of course, usually we have no access to new unseen data, because if we would have more data, then, well, we would just use this for training a better model, right? So that's the fundamental, or one of the fundamental problems of supervised learning, that we want to use all the data we have for training a good model, but then we have no test data left to see how good the model is, actually. So what we can do is we divide our data set manually into dtrain and dtest and use the latter, so dtest, to estimate the generalization error via some metric rho, which I will tell you more about in the next slide. So what we do here is we divide the data we have, which is the union of these two tables here, dtrain and dtest. We divide it in two parts, training data and test data. Then we use the first part, here the training data, to learn a model through the learner and get a best model f hat of x. Okay, that's the output of the empirical risk minimization, for example. Then we use this trained fixed model, feed in the new test data, and compare y and y hat, for example. So we compare the prediction of the model and the true values with some metric. So what is a good metric to compare predictions of a model and true target or true labels? We could use the inner loss function. That's always possible, and you can do this. Nevertheless, there can be perhaps cases where this is not ideal and where we can construct other metrics other than the loss function, which have perhaps better characteristics, depending on what we want to do. So for both classification and regression, there is a large variety of evaluation metrics, of which we will just cover a fraction, and of course just a fraction of this fraction in this nutshell chunk here. So let's start with classification. Here are some very common evaluation metrics. The first one you've probably seen before is the accuracy, which is defined as you see here. It's the mean of some indicator functions. So this thing here is, so this thing in the square brackets, so that part, let's say, is 1 if the true label is the same as the predicted label. So basically if the classification is correct, and 0 if this is not the case, so if the classification is not correct. So the accuracy should be high. It would be 1 if all the classifications, all the predictions would be correct. And the worst case is 0, that all the predictions are wrong. The exact opposite of this is the misclassification error, which just switches the equal sign by the not equal sign. So guess what? Misclassification error is 1 minus accuracy. It's a proportion of incorrectly classified observations, but it's basically the same idea. Then we have two other metrics here for you. These are the Breyer score and the log loss, which have a different idea because they do not compare y and y hat, but y and pi hat. So here we compare the predicted probability of the model with the true label, with basically the L2 loss. But we can also use the log loss or Bernoulli loss, which you already know from logistic regression, and just use this as evaluation metric. The advantage of these evaluation metrics is that false confidence is penalized more heavily. So imagine a case where the threshold for classification C is 0.5, which means that if pi hat is, pi hat is larger or equal than C, then we say y hat is 1, and if it's smaller than C, then we say y hat is 0. Okay, that's the definition of the threshold. And imagine now that you have an observation where pi hat perhaps is 0.55 and the true label y is 0. So of course then we have a wrong prediction because y hat would be 1. That's larger than 0.5. But it's not that wrong, okay, it was a close call, let's say. But if on the other hand the predicted probability is 0.95 and the true label is 0, that's far worse, okay? So this is mirrored in both the Breyer score and log loss. Okay, and then some other metrics are based on the confusion matrix. You see here an example of the confusion matrix. In the columns you have the true class y, in the rows you have the predicted class y hat, and you can compute just a real high number of conditional probabilities here. So for example, if you divide the true positives by all the observations where we predict the positive class, then we get precision. And on the other hand, if we divide the true positives by all the values by all the observations which have as true class, the positive class, then we get the recall. And There are other metrics that we can compute out of this, for example, the accuracy, of course, and the misclassification rate. Accuracy is here, or the false negative rate, or false omission rate, or whatever. There are, as I said, a lot of different metrics, and we will treat those in detail in the deep dives on the confusion matrix. So for now, you can just accept that there are different metrics and that there are many names for sometimes the same metric. So for example, the true positive rate is also called recall, is also called sensitivity. So that's exactly the same thing, just 3 names for the same conditional probability. Okay, then as last part for the classification matrix, we have the ROC curve. The ROC curve, just in a nutshell, again, plots the false positive rate against the true positive rate. So it would be great to have a false positive rate of 0, okay, no mistakes here, and the true positive rate of 1, so everything perfect here, which would be the upper left corner. So we would like to have a classifier which is here, and what the ROC curve visualizes, plots, is the true positive rate and the false positive rate for varying thresholds. Okay, so for varying the threshold C, so with higher threshold C, less observations are classified as positive, and for smaller thresholds C, more observations are classified as positive. And we can try to find the best threshold by looking at the ROC curve. And we look at values where there is no combination of true positive and false positive rate, which is better than this. Okay, so these 4 blue circles here are in that sense optimal. So none of these 4 is better than the other 3 of those 4, because either the true positive rate or the false positive rate is better or worse, respectively. And as last thing, you can compute the area under this curve. And if this area is high, if you got classifier, and if it's just 0.5, it's just random guessing. Okay, then let's see some metrics for regression. Perhaps you already know the sum of squared errors, just the sum of the squared residuals, y minus y hat. You can take the mean instead of the sum, then you have the mean squared error. You can take the square root of the MSE, then you have the root, mean squared error. You can also compute the R squared value or the mean absolute error, which is just using the L1 loss and then taking the mean of all those L1 losses on test. Okay, so now we have seen evaluation metrics for classification and for regression. And now the question is, how can we improve, perhaps, or can we improve the estimation of the generalization error? So what we can do, or what we do with this split strategy that I showed you before for train data and test data, is that we just estimate the generalization error via taking the mean of the loss values for some test data set. Okay? So we compute the selected metric for each observation and test set and compute the mean. It's as simple as that. This is okay-ish. The problem is that if we have a rather small data set, we don't really want to set apart tests or set apart observations just for estimating the generalization error. Okay. So perhaps we have just a very few test observations, so a small m, but then the estimation will be unstable or will have high variance. So we would like to have a higher number of test observations m, but the problem is that this decreases then the amount of data that we have left for training the model. Okay. So a different option is to compute the estimate here for multiple test sets and then to aggregate them. So that's exactly what we do when we speak about resampling. So we do not have access to infinite data. We cannot really increase m unless we accept that then the trained model is worse because there is less data left for training the model. So what we try to do is we just do perhaps more train test splits, okay? Not just the one. We do several train test splits, perhaps in total a number of B train test splits, via subsampling, cross-validation or bootstrap, which you will all of those see later in more detail. And then we compute the estimate of the generalization error for each test set and aggregate the estimates. Okay, and this stabilizes the estimation of the generalization error also for small data sets. As said, all these methods aim to generate the train test splits by splitting the full data set repeatedly. Then we train on train, we test on test, and aggregate somehow the test results. You see here one visualization of threefold cross-validation, and we go over this in detail in the specific chunk on resampling. So just as a first teaser of this, here we have threefold cross-validation, which means we divide the data set into 3 parts. So let's say this is the entire data set. We divide this into parts 1, 2, and 3, which are used 3 times. 1, 2, 3, 1, 2, 3, 1, 2, 3. And what we do is that in these iterations, 1, 2, and 3, we always use one part of the data as test. In the first iteration, it's this data set, and we use the remaining data points for training a model. Okay, so we train the model on, in this case, 1 and 2, get a trained model, then we predict the test data set with this trained model and get an estimation for the test error. We do the same thing for testing on Y and training on testing on 1 and training on 2 and 3. And for testing on 2 and training on 1 and 3. Okay, then we get 3 test errors and we take the average of this. Okay, that's it for evaluation in a nutshell. See you in the next video.